Okay, so what do we know right now about the nucleus? Well, we know it has a positive charge. Because the nucleus is made up of protons and neutrons. Neutrons are neutrally charged, so protons are the ones that carry that positive charge. We also know that the nucleus is very dense. And the nucleus is packed very tight. Okay, and also the last thing is that the nucleus is very small as compared to the rest of the atom. Okay, so based on what those three facts, that it has a positive charge, it's very dense and very tightly packed, and that the nucleus is very small as compared to the rest of the atom, what can we conclude about the stability of the nucleus? Well, not a whole lot. Based on those three facts, not a whole lot that we can really conclude about the stability of the nucleus, but there leads another question. And here's the question. It depends on how many neutrons we have in an atom. If we can answer that question, then we can start talking about stability. Now, predicting the behavior of isotopes is difficult, but we can make some generalizations. So let's take a look at this table over yonder. So in this table, let's say for an atom, you've got an odd number of protons and you've got an odd number of neutrons. Now, the number of stable isotopes having an odd number of protons and an odd number of neutrons is 4. Okay, but if we have an odd number of protons and an even number of neutrons, that number goes from 4 to 50 stable isotopes. Okay, now what if we make the number of protons even, but we keep the number of neutrons odd? In this case, we have about 53 stable isotopes, so just a little bit more than having an odd number of protons and an even number of neutrons. Okay, but look at this. If we have an even number of protons and an even number of neutrons, we have 164 stable isotopes. So what can we conclude from this nature? It's telling us that nature prefers even numbers. And that most likely, if you have an even number of protons and an even number of neutrons, you're very much likely going to be a stable isotope. Now, let's take a look at what happens with the ratio of neutrons to protons. So in this picture, what we're looking at on the left-hand side, on the y-axis, is the number of neutrons. On the x-axis, we're looking at the number of protons. Okay, and this red line right here, what this is indicating is that if you take the number of neutrons and divide it by the number of protons, so you try to find the slope of this line, this is going to be equal to 1. So this is like the graph y equals x. All right, and what we're looking at, these isotopes seem to be following, and these red dots are indicating different isotopes. These red dots seem to be following along that red line up until you get to this point right here. Okay, it seems like once you get past 20 protons, that line starts veering off a little bit. Okay, but the number of isotopes are pretty much keeping together, and so graphing all the known isotopes in this format gives us this item called the belt of stability, where all these isotopes inside this belt of stability are stable. So these are stable isotopes. And if you go outside of that outside of that belt of stability. Let's say you decrease the number of protons, or you increase the number of protons, or you decrease the number of neutrons, or you increase the number of neutrons. Whichever way you go, anytime you leave this belt of stability, that's when you become unstable or radioactive. Okay, so the stable isotopes are located in this area of the graph called the belt of stability. Most radioactive isotopes are above or below this belt. And it looks like the number of neutrons divided by the number of protons is greater than 1, but the difference doesn't get too high. So even though it's veering off of this red graph here, or this red line, it's not veering off terribly. So it's still pretty close to that ratio of, just being a little bit above 1. Now, how does an isotope become stable, or how does it go from being outside the belt of stability to being inside? Well, the first thing is that if you're above the belt of stability, you're going to have to reduce the number of neutrons divided by the number of protons by going through a beta particle emission. And so what that means, if you take a neutron, okay, a neutron can actually break down to give you 1 proton and 1 electron, or a beta particle. So that's called beta particle emission, because you're emitting or giving up a beta particle. You trade 1 neutron in, and you get 1 proton, 1 beta particle. Now, if you're below the belt of stability, you have to increase the number of neutrons to protons by going through positron emission. So in this case, we're going to take a proton, we're going to cash a proton in to get a neutron out, and a positron. Now, it's also possible to undergo something called electron capture, where you're taking a 1s electron and it's captured by the nucleus. And the proton will combine with the electron to form a neutron. This allows the atomic number to decrease while the mass stays the same. And so an example of something like this is like, let's say you take iron 55, okay, which has an atomic number 26, and you react that with an electron or a beta particle. That's going to give you manganese 55. Okay. Now, to give us a quantitative measurement, so this is all well and good. We're not really doing anything complicated in terms of math. We're just looking at this and trying to figure out. We're looking at this graph and going, well, we're here. How do we get into there? Okay. We can look at this from another point of view by measuring something called the nuclear binding energy. This is the energy required to break up a nucleus into protons and neutrons. And this value represents the conversion of mass to energy that occurs in exothermic nuclear reactions. And the concept of nuclear binding energies came from the discovery that the masses of nuclei are always less than the sum of the masses of all the nucleons. So the sum of all the protons and the neutrons of a nucleus. And the difference between the atomic mass of an atom and the sum of all the masses of protons and neutrons is called the mass defect. Now, relativity theory says that the loss in mass between the two shows up as energy that's being given off to the surroundings. And this led to Einstein's really famous equation that says that energy is equal to E equals mc squared, where E is the energy that's measured in joules, m is mass measured in kilograms, and then c is the speed of light squared. All right. Now, however, if we know that the energy and the mass are changing, So that means that the final value is not as the same as the initial. We can write this, that the change in energy is going to be equal to the change in mass times the speed of light squared. Okay, and this is usually the form of Einstein's equation that we use in chemistry. And so the units for energy, when we solve for this equation, are going to be AMU times meters squared over second squared, which we need to convert to joules with the following conversions. That 1 kilogram is going to be equal to 6.02 times 10 to the 26th AMU. And that 1 joule is going to be equal to 1 kilogram times meter squared over second squared. Now, that being said, it's more meaningful to see how the nuclear binding energy per nucleon. So the way that we can calculate that, if we want to know the nuclear binding energy per nucleon, the way we would do that is take the nuclear binding energy and divide it by the number of nucleons. Now, the number of nucleons, what this is telling us, this is the number of protons plus the number of neutrons. And this value allows us to compare the stability of all nuclei on a common basis. And what we're looking at in this picture, on this graph, we're seeing that as the mass number goes up on the x-axis, we're looking at nuclear binding energy, and so this gives us another form of that belt of stability. All right, so that leads us to our problem. So here's our problem: calculate the nuclear binding energy in joules, and then the nuclear binding energy per nucleon of bismuth 209. Which has a mass of 208.9804 AMU. All right, so before we get really into this, if we look up bismuth on the periodic table, we know, or based on the numbers given to us, we know that it's got to have 83 protons, and in order to have a mass of 209, it's got to have 126 neutrons. And adding these two values up together, we get 209 nucleons. Okay. Now, if we were to figure out the mass of bismuth out of this atomic number, or if we take the number of neutrons, so you have 126 neutrons, and we multiply that by the mass of one neutron, which is 1.008665 AMU. These two numbers together gives us a mass of 127.09179 AMU. Okay, and if we take the 83 protons and multiply it by the mass of one proton, which is 1.007825 AMU, these two numbers together gives us 83.649475 AMU. Now, if we add up these two numbers together, the 127.09179 plus the 83.649475, that gives us a grand total for the masses of everything, 210.7413 AMU. Okay, so that's the masses of all the protons and all the neutrons inside bismuth 209. Okay, but the atomic mass that's being reported for this particular isotope is 208.9804. So there's a difference in mass, and remember that that's what Einstein said, that difference is because you've got energy. Okay, so to help us determine that mass defect, the change in mass, okay, where delta M is going to be equal to the atomic mass minus the nucleon mass. Okay, so the atomic mass was told to us as 208.9804 minus the nucleon mass, which we calculated to be 210.7413 AMU. that difference is going to give us a negative 1.7609 AMU. So this is our mass defect. Okay. Now to calculate what that energy change is going to be, using the Einstein equation that delta E is going to be equal to delta M C squared, we know what delta M is because that's going to be the negative 1.7609 AMU times the speed of light, 3.0 times 10 to the 8th meters per second, and that's going to be squared. Okay, delta E comes out to be negative 1.585 times 10 to the 17th AMU times meters squared over second squared. Now, we need to convert AMU, because that doesn't really mean a whole lot to us, to kilogram. And we have that conversion factor that 1 kilogram is equal to 6.02 times 10 to the 26th AMU. Okay, so now delta E should come out to be negative 2.6325748 times 10 to the minus 10th kilogram times meter squared divided by second squared. Now, kilogram meter squared divided by second squared, that's pretty meaningless to us. We need to convert this to joules. It turns out that 1 kilogram meter squared per second squared is equal to 1 joule. So this number is the same as saying negative 2.6326 times 10 to the minus 10th joules. And so this is the nuclear binding energy. Okay, now if we wanted to figure out how much, if we were to take this value, the negative 2.6326 times 10 to the minus 10th joules, and we divide it by the number of nucleons that we have, 209 nucleons. If we take this number, the negative 2.6326 divided by 209, that should give us 1.26 times 10 to the minus 12th joules per nucleon. So this is going to be the nuclear binding energy per nucleon. Now, why? Why do we really care about these numbers? Where is this all coming from? So this explains a lot of quite a few things to us. Okay, so this number, this explains what's really keeping these protons and neutrons held together. It takes this much energy, this many joules per nucleon, to hold all the nucleons together. And then this number, this is holding everything together. Okay? The reason why this is so cool is that this was one of the first stepping stones, or one of the first stepping stone calculations that scientists had to do in order to figure out how much uranium or how much plutonium to use in the first atomic weapons back in the Manhattan Project.